Types of solutions. We talk a lot about aqueous solutions. Those are probably the most common. In an aqueous solution, the water is the solvent. But the solute could be a gas, a liquid, or a solid. And you can have solutions between 2 solids, 3 solids. You can have solutions of a solid, a gas dissolved in a solid, any combination. And so here's some examples. Solid solutions, the ones we're most familiar with, are alloys. So brass is a solution of copper and zinc. It's a homogeneous mixture of those 2 metals. But it's not a compound because the amount of copper versus the amount of zinc can vary. So let's talk some more about this idea of the mixing. So we know that a lot of physical systems tend towards lower potential energy. That's why boulders roll down hills instead of up, because they're going to lower potential energy. When we form a solution, that does not necessarily lower the potential energy of the parts of the solution. So if we look at 2 noble gases, 2 ideal gases, we've got neon and we've got argon in a container. And we remove the barrier between them. We know from kinetic molecular theory of gases that these guys are bouncing around, and if that barrier is gone, they are going to continue bouncing around and they're going to mix, right? Does that affect their potential energy in any way? No, it doesn't. So mixing of 2 ideal gases does not lower their potential energy. Something must be driving this mixing. And that thing is called entropy. Entropy is a way of measuring energy randomization or energy dispersal in a system. The tendency of energy to spread out. So when we have those 2 gases mixing, the kinetic energy of each of the gases becomes spread out over a larger volume. So that increases the entropy. So substances mix due to the pervasive tendency for energy to spread out whenever it is not restrained from doing so. This also explains how thermal energy flows from hot objects to cold objects. You take a hot piece of metal and you put it in a pot of cold water. Heat travels from the hot piece of metal into the cold water. Why? Because the thermal energy spreads out. And that is a thing that is favored by the universe. Energy spreading out. Intermolecular forces have a big effect on solutions. They can promote the formation of a solution or they can prevent it. And we've just talked about intermolecular forces. So here we have 2 nonpolar molecules, and they are attracted to each other by dispersion forces. It's kind of a review for the exam today, too. Here we have 2 polar molecules, and they're interacting by dipole-dipole forces. The attraction between the positive end of one polar molecule to the negative end of the other polar molecule. Hydrogen bonding we can get if we have nitrogen, oxygen, or fluorine bonded to hydrogen in a polar molecule. And then we also have ion dipole forces. The attraction between a cation and the negative ends of water molecules, or an anion in the positive ends. So those are the types of intermolecular forces. Yes?
Ion dipole, was that polar and nonpolar together, or?
Ion dipole is between 2 different compounds. So that makes it kind of different than the other 3. So you can't have ion dipole forces within a pure substance. It will be between a polar substance and an ion. And it happens mostly in aqueous solutions. So when we look at a solution forming, we have 3 different types of interactions to consider. We have the interactions between solvent molecules. We have the interactions between the solute molecules. And then we have the interaction between a solvent molecule and the solute molecules. And the relative strengths of these are going to determine whether the solution forms or not. So if the interaction between the solvent and the solute is strong compared to the solvent-solvent or solute-solute interactions, then a solution will form. If the solvent-solute interactions are even the same as the interactions between solvent particles with themselves and solute particles with themselves, then a solution will form. So I think I mentioned my analogy of a room full of Japanese and Swedish people, right? And they don't speak English, they just speak Japanese or Swedish. Well, if the Japanese people, say, are the solvent and the Swedes are the solutes, is there going to be good interaction between them if they don't speak the same language? No. And they're not going to mix. So here the interactions between solvent and solute are very weak. The interactions of the Japanese people with themselves, with other Japanese people, they can communicate just fine. The Swedish people with themselves, they can communicate just fine. They are not going to mix up. They're going to stay in little clumps or even half on half, right? If you bring in an interpreter or if you make the people bilingual, then the interactions that the Japanese and the Swedish can have with each other become either equivalent or possibly greater than what they have with themselves, and then things will mingle and mix up. Does that make sense? So let's look at a practice question here. Determine whether each compound is soluble in hexane. What is hexane?
Nonpolar alkane.
It's a nonpolar alkane. How many carbons does it have?
6.
6. So let's just draw it. So 6 carbons, and is going to have hydrogens on it, and it's just going to have enough hydrogens that we can have. I'm just trying to make an H.
Like 14.
Yeah, it'll be 14. We'll have enough hydrogens that each of the carbons can have 4 bonds, because the ane suffix tells us that it only has single bonds. The hex prefix tells us 6 carbons. And that's messy, but gets it done. So this is a nonpolar molecule. What kind of intermolecular forces is it capable of?
Dispersion.
Dispersion. It can only have dispersion forces. Dispersion forces are the weakest, right? So we're going to look at water. What kind of intermolecular forces does water have?
All the way up to hydrogen.
Yeah, it's got dispersion forces, dipole-dipole forces, and hydrogen bonding. Are the interactions between water molecules greater than the interaction between water and hexane?
Yes.
Yeah. So water is real happy interacting with itself. It doesn't want to lose those interactions to have a weaker interaction with hexane. So is this going to form a solution?
No.
Nope. Not soluble. How about ammonia?
Same thing. All the way to hydrogen.
Same thing. Ammonia has hydrogen bonding, which is strong. Ammonia, hydrogen bonds with other ammonia molecules. Very strong interaction. The interaction between ammonia and hexane can only be dispersion forces because hexane is only capable of dispersion forces. So that weak interaction says this will not be soluble. How about propane?
Dispersion.
I always have to say, Mom eats pickles. Mom eats pickled bananas, that's how I remember that. Propane. This is nonpolar also, right? So this only has dispersion forces, weak dispersion forces between the propane molecules, and propane will interact with hexane using weak dispersion forces. And so the interactive forces are about the same strength as propane with itself or hexane with itself. And so they will mix because there's no loss in potential energy by doing that. So this will be soluble. How about hydrogen chloride with hexane?
That's polar.
So hydrogen chloride.
I can tell if something's polar.
Okay, so this is, how do you tell if it's polar? This is a diatomic molecule. 2 atoms. If the bond is polar, the molecule's polar. Well, do hydrogen and chlorine have the same electronegativity? No. Probably not, right? So this is polar. Polar molecule has dipole-dipole forces that are stronger than the dispersion forces it can have with the hexane. Is this going to dissolve? Nope. Any questions?
So it has dispersion and it has dipole-dipole?
Yes,
And why is it dipole-dipole?
because it's polar. Dipole-dipole forces are the interactions between the permanent dipoles on polar molecules. Hydrogen bonds are super dipole-dipole forces because the dipoles are especially strong. And dispersion forces are the attraction between temporary dipoles on nonpolar molecules and atoms. Everything has dispersion forces. Everything polar has dispersion forces and dipole-dipole forces. And things like water and ammonia have dispersion forces, dipole-dipole forces, and hydrogen bonding.